If you think of any object, from a cup of tea to an ice cube, it will constantly be absorbing and emitting electromagnetic radiation with its surroundings. Whenever it absorbs radiation, it will get warmer, because radiation is pure energy. Whereas when it emits radiation, it will cool down. This means that the balance between absorbing and emitting radiation will affect the object's temperature. For an object like our cup of tea, which is hotter than its surroundings, more radiation will be emitted than absorbed. So overall, it will lose energy and cool down. For an object like our ice cube though, which is cooler than the surroundings, less energy will be emitted than absorbed, and so it will slowly warm up. If an object absorbs and emits the same amount of energy though, then it will stay the same temperature, because it's gaining and losing the same amount of heat. Electromagnetic radiation comes in a range of different types, and we now need to take a closer look at what determines which of these types is emitted. First though, you need to understand the term intensity, which is the power of the radiation per unit of area. So effectively, it's a measure of how much energy the radiation transfers to a given area in a certain amount of time. We can use this concept to draw ourselves a graph of the emitted radiation. On the x-axis, we have the wavelength of the radiation that's emitted, and on the y-axis, we have the intensity. So basically, the graph shows us how much of each wavelength is emitted, because the higher the intensity, the more of that wavelength must be being emitted. Now, for this topic, we only need to worry about ultraviolet radiation, visible light, and infrared radiation, which go from left to right along the x-axis, because it's in order of increasing wavelength. If we took a random object at room temperature, like a paper bag, and we plotted how much of each wavelength is emitted, then the curve would look something like this, because most of the energy it emits is in the infrared range, and because it's not very hot, it doesn't emit very much radiation at all. If we took a much hotter object though, like a piece of burning coal, then its curve would be shifted up and to the left, meaning that it emits more radiation overall, and that it emits shorter wavelengths than the bag. For an even hotter object, like the sun, it would be shifted up and left even more. So the takeaway from this is that as the temperature of an object increases, the intensity of every emitted wavelength increases as well, which is why the curves get higher. But the intensity of the short wavelengths increase more than for the longer wavelengths, which is why they seem to shift to the left. This also explains why the color of Bunsen burner flames change as they get hotter. The hotter the flame, the shorter the wavelengths of light emitted. So the color changes from an orangey red to blue. For objects at room temperature though, the emitted radiation is all in the infrared range, rather than visible light, which is why we can't see the emitted radiation. The last thing we need to cover is that the balance between absorbing and emitting radiation also applies to our entire planet. The Earth is constantly being bombarded by electromagnetic radiation from the sun, and is also emitting its own infrared radiation, because it's basically a big warm object. To make things more complicated though, the Earth also has an atmosphere, which can also reflect, absorb, and emit radiation. During the day, more energy is being absorbed by the Earth and atmosphere than is being emitted, which increases the local temperature. Whereas at nighttime, less energy is absorbed than emitted, and so the local temperature decreases. Overall, though, some part of the Earth is always in the sun, so the overall temperature stays pretty constant.